All right, so here's kind of the last big thing dealing with momentum, specifically angular momentum. And this is this concept known as moment of inertia. So, hypothetically, if I ever retire, and they said, hey, you can come back and you can give one lecture out of the entire Physics 1 curriculum, you get to come back and give one lecture. This would be the lecture I would give. Mainly because a whole bunch of kind of random things will all make sense at the end. Okay, so when you talk about moment of inertia, it's related to inertia, but it's like a second cousin, okay? So when you talk about inertia itself is only dependent upon one thing. Luke Etheridge, what is the one thing that determines inertia?
What, mass?
Mass, okay? If I have this little pencil and I have a 1 kilogram mass, this 1 kilogram mass is always going to have more inertia than this pencil does, because there's more stuff in it. Simple. More stuff, more mass, more inertia. Harder to get it to move, but once it's moving, it's harder to get it to stop. Now, moment of inertia is a similar type idea. The moment of inertia is trying to make something spin, okay? Something spin about an axis, whether it's a door, a rod, a wheel, the earth, the moon, whatever it is. So basically, it's the same idea. The bigger the moment of inertia is, the harder it is to get it to spin. But once you get it spinning, the harder it is to get it to stop, okay? So it's the same idea. But here's the difference. When you look at moment of inertia is based upon two things. It's not only based upon mass, but it's also based upon where that mass is located in terms of trying to make the object spin. So, here's the deal. On your equation sheet, or on that sheet that I gave you yesterday, that sheet of lecture notes, on the back side of that, there's a whole bunch of different objects that have different moments of inertia. Solid cylinder, hollow sphere, solid sphere. And then also on page 210 of your book, there's a whole chart of different objects with different moments of inertia. But what they all have in common is that some form they have mr squared, okay? They might look completely different, but at the end of the day, it's some mass times the radius squared, okay? That's what they all have in common. There might be fractions, a whole bunch of other things, but at the end of the day, they all have this in common, that it's mr squared. Now, if you look, there's two situations, and only two, where you can actually use mr squared to find the moment of inertia. Situation number one, you have a thin hoop. And in the problems, it has to tell you, hey, this is a thin hoop. This is a solid sphere. Treat this thing as a point mass. It's a, whatever it is. You have to be told in the problem what the object is, and they have to give you the dimensions. So, if you have a thin hoop or a point mass, so for example, if I take this rubber stopper and move it, swing it around over my head like this would be an example of a point mass. So this would be the mass of the stopper, whatever the radius is. The moon orbiting the Earth. You treat the moon as a point mass as it goes around the Earth. You can treat the Earth as a point mass as it goes around the sun. But it forms a general idea of mr squared. So with that said, Mitchell, what are the units going to be for any moment of inertia? Do not make this difficult.
Kilograms per meter
Nope,
squared?
not per.
Or meter squared?
Yeah, it's just kilograms meters squared. There's nothing flashy about that. It's just smash mouth units. Kilograms meters squared. That's what you've got, okay? There's nothing else. You can't fancy that up and go, oh, Newton second. No, it's just kilograms meters squared. So with that said, I've got a aluminum rod with a couple of brass slugs on the end of it. And I'm gonna try and balance this thing. Situation number one, I'm gonna try and balance it with the masses at the bottom. Situation number two, I'm gonna try and balance it with the masses on the top. So here's the question. In which situation is it gonna be easier to balance? Slugs at the bottom, slugs at the top. So how many vote slugs at the bottom? Okay? How about the slug at the top? Deacon, you're on that train. So, Sam I am, come up here. Put your athletic prowess to the test.
Yeah, sure.
I got faith in you. Okay? So, first thing, put your hand out flat. You can take the other hand and hold it. And I want you to try and balance that rod. You can move your bottom hand. You can do whatever you need to do to try and balance it. Tough to do?
Yeah.
Flip it over. You can move your bottom hand.
Oh, you don't want it to stay still?
Yeah, it has something to do with the radius.
Oh, God!
Oh, medic!
It's basically
It's okay.
I think it's your blood draw.
All this time you've done this. No one has ever hit me with it. Okay?
Hey, first to do.
Thanks, Chuck.
And it's on video.
And it's on video.
And it's on video.
Let's go.
So, Chuck, which one's easier?
This one.
That one. Okay?
Thank
And
God.
because-
Much easier. And here's the reason why. Thank you, in spite of the bruise I'm going to have. So, here's the story.
Cooked.
When you try and balance this, what do you want the angular velocity of the end of this rod to be?
0.
0. Okay? You don't want it to accelerate. So, if you look at this mathematically, I don't change the mass of the system. The mass is the same, right? But when I put this out with the slugs at the top, what's going to happen to the radius of where that mass is located?
Radius rises.
Radius gets bigger, therefore the moment of inertia gets bigger, therefore it's harder to get it to move. So if I do this without hopefully hurting anyone, so if I put it like this, I can pretty much balance this like all day long, okay? Right? If I try and do that same thing like this, it's much more difficult to do because the end, because it doesn't have as much mass, is easier to speed up or slow down. Luke, have you ever tried to balance a baseball bat?
Many times.
What do you, which one's easier? With the barrel at the bottom or the barrel at the top?
I
Huh?
always use the knob.
Barrel at the top, why?
Yes, yeah, that's what I meant.
Because of that equation right there. That's why. Okay, now, Dylan, come up here. Don't hit me,
Take
okay?
a step away.
So on Dylan, here's what I want you to do. I want you to hold it like this, go back and forth. And then hold it like this and go back and forth. Tell me what you experience. Okay, now flip it over.
Alright.
Is there a difference?
Yes.
What's the difference?
This one's a lot more wobbly.
Why?
I imagine because the weight's farther from you.
Okay.
That's best thing to describe it.
Okay, so if you look with this out here on the end, right? Again, it's the same idea. You've got all this mass out here on the end. So it's tough to get it to move, but once you get it moving, it's
So,
hard to stop, right? Because it wants to keep moving because it has a lot of stuff. Like this, there isn't much mass. I can move this back and forth very easily. Well done, thank you. All right. Shut down the camera. Let's go to the back.